Hey everybody, today we're going to be talking about refraction of light. It sounds like reflection of light, but it's somewhat different. In reflection of light, you have light that is bouncing off of a surface, a reflective surface. However, in refraction, you have light that is trying to pass through another medium. And some stuff happens when you pass through another medium. So let's just jump right in and get to the details. You can see that definitely there's a prism that's shown on this front slide, and definitely prisms have something to do with what's going on with refraction. Okay, first of all, let's talk about what refraction actually is. It's a phenomenon that happens when light, or for that matter any EM wave, but we're going to specifically talk about light, enters a new medium. You do know that light travels at the speed of light in a vacuum, pretty much the same speed in air, but not in any other medium. It gets slowed down pretty substantially by any other medium or anything that's other than a vacuum, which means that even when light goes into air, it gets slowed down a little bit, just a tiny percent of really just a small percent of the speed. It really is barely noticeable, although it is measurable as it turns out. However, when it goes into glass or water, it gets slowed down somewhat more dramatically. Let's see what that's all about. I want you to imagine an analogy. It's one of my favorite analogies. You know, I'm not a big fan of analogies for physics. I don't think they always work, but this one kind of does. If you imagine going to the beach, you get out of the car, especially when you're a kid, and you start running. You know, you can run pretty fast on the pavement, but once you hit the sand, you immediately slow down, and the steps, or I guess you can say the distance between your strides, between your steps, gets smaller. And then, of course, if you hit water, you slow down even more. Now, as it happens, light exhibits some pretty similar behavior. It's a little bit weird at the surface, and we're not going to worry about that. That's for you people who ever investigate advanced optics as a physics student. You'll get into that, but we're not going to quite talk about that. So here it is animated. On the left, we have what you might call a fast medium. On the right, you might have we'll call it a slow medium. On the left, that would be something like air. And on the right, it's going to be maybe going into water. So a couple things that you notice. You notice that the speed changes. It's definitely moving slower on the right. But you probably also notice that the wavelength changes. It goes from a particularly, like a long wavelength on the left to a much shorter one on the right. But something actually stays the same, and that is the frequency. The frequency stays the same. Now, why is that? Well, the frequency is basically set by, whatever process creates the wave to begin with, whether it's maybe your hand that's kind of like tapping out waves with a ruler or something like that, or it could be an atomic process that's generating light. But the frequency has no reason to change. The frequency, as you may learn later, is a measure of the energy of a wave, a light wave. Or you actually may have learned that in chemistry before. But the frequency and the energy have no reason to change. However, going from one medium to a new medium, since the speed goes down, then the wavelength also goes down. The equation that's depicted above, lambda equals speed over frequency, is really just another way of writing speed equals frequency times wavelength. So here's what's going on. The speed changes. Light travels from air to a more dense medium like glass, plastic, or water. The light is going to be slowed down. And of course, it works in reverse. Now, the frequency is set by whatever process makes the light, has no reason to change. Going back to the wave equation, velocity equals frequency times wavelength. If the speed changes but the frequency does not, then the wavelength has to change. Speed goes down, wavelength goes down. Speed goes up, wavelength's got to go up. Here it is animated again, same sort of thing. You notice that there's some numbers there, N1 and N2. N2 is significantly greater than N1, and we're going to learn to call that an index of refraction, which is a way of describing how much light is slowed down. You could look at this kind of overhead if you want to imagine it this way. Wave fronts are coming in from the left, almost like you're tapping a ruler in water. It goes into a more dense medium. Let's say you're going from air into glass, and then it comes back out and gets back to, everything goes back to the regular again. Also notice this dotted line here. That is what we call the normal line or perpendicular line. So that's an overhead view could be an overhead view of water waves or light waves. In any case, they're moving to the right, although it actually works moving to the left as well. As they enter the glass, they get slowed down. Once they leave the glass, they speed up again because the frequency can't change, so the wavelength has to. And again, the wavelength will get smaller as it goes through the glass because the speed gets smaller. Again, of course, the reverse happens as well. Let's take a look at this animated a little bit. So here's a light laser. Let's take a look at waves here. Let's turn this on. You can see right here that the waves are getting closer together. If I bend this, you're going to get some bad animation effect here, but definitely they're getting closer together, and they happen to be slowing down, but also notice that there's a bend here. So let's talk about what this bend is all about. We can see the bend pretty prominently if I just switch it into raise. Oh my gosh, there's definitely a bend. That angle and that angle are not the same. So what is that all about? Let's get back into this. Okay, so the bend. Here's an example of or an analogy also can be kind of helpful. Let's say that you have a car that comes in from pavement into a muddy surface. And if you're looking overhead, there would be the passenger side front tire that hits the mud first. Well, it gets slowed down a little bit, and as a result, the car gets twisted this way. Now, light does something very, very similar. While it's getting twisted, this wheel over here is continuing to go to the right. So this part's going a little faster than that one is. You end up getting the car turning right here. You actually have something very similar that happens, but in the opposite way when cars hit ice. Now, if this car had been coming in straight in, like from the top down to the bottom here, then both wheels would get slowed down by the same amount. But in this example, they're coming in at an angle. That's why we see a bend when the light goes in at an angle, but not when it comes in straight. It's slowed down in both cases, but the bend only happens when the light goes in at an angle. The angle absolutely makes a difference. We're going to come up with a way of computing exactly the effects here shortly. Again, if the angle is not zero, the refracted angle will be different. Also, it's going to be smaller than the initial angle if the new medium is more dense than the original one. Now, the dotted line that's shown above is what we call the normal line or a perpendicular line, and we measure angles from that line. There it is, seen with lasers. You saw this in the lab. Initial angle here, refracted angle here. Notice that that is smaller than the initial angle. So to summarize, if light goes in at an angle, it bends toward the normal or perpendicular line. Going back here, instead of continuing straight, it bends toward the normal line. When it exits, it bends away from this new, what would be a new normal line here. I'm going to show you this slightly better here in a moment. Yeah, it's the exact opposite effect going from more dense to less dense. The light rays bend away from the normal line. Here we have it. This is probably a more understandable picture. So the surrounding area would be air, and this would be glass or plexiglass. Initial angle here, refracted angle. Everything, all the angles are measured with respect to a line that's normal or perpendicular to the surface. Initial angle, refracted angle, which is smaller in this new, more dense medium. Now it comes down to the bottom of this rectangular piece of plexiglass. Here's our new initial angle, and here's the new refracted angle. So there's the new initial angle, and the new refracted angle is bigger than the original one because it goes back into air. Something similar happens here, but it's less obvious because you have to actually imagine a normal line that's perpendicular to the surface. So instead of continuing straight, a laser would get bent that way. So just to give you a little bit of practice seeing this, again, instead of continuing straight, it bends toward the normal. When it comes out here, it bends away from the new normal line. This is a little bit different. It's going to hit here, but we have to draw in a normal line. I'm going to do that right there. It bends toward the normal line. Over on the right side, there's a new normal line here, and it bends away from it. It gives you kind of your classic prism behavior. This is strange. This is coming in straight. So continue straight because there's no initial angle. But over here, it's going to hit this side. Here's our new normal line. It's going to bend away from it. Lenses. You saw this in the lab. This is strange. We have to actually imagine normal lines anywhere you have light rays hitting the lens. This is a convex lens surface. I didn't actually draw them in here. I'll get to that a little bit later. But what you saw in the lab was it bends here, and then it bends more upon exiting, and that's because of the symmetrical shape here. It's curved this way, then curved that way. We end up getting the opposite effect where it continues to bend toward what we're going to learn how to call a focal point. More about this shortly. The opposite thing happens with a concave lens. the light rays end up bending outward. We'll look at that in greater detail shortly. Now, the reverse is also true. You're going from water into air. The light bends outward with a greater angle. We're going to ultimately learn how to quantify this, but there's a thing called a critical angle where the light just skates across the surface of the water. And if you go with an initial angle any bigger than that, then you get total internal reflection. There's much more to be said about this. So it's basically how fiber optic cables work. You have light going, not from, in fiber optic cable, it's going from plexiglass or fiber optic into air, but with water, it's kind of easier to visualize. So you have a laser that's going up here. You're at the critical angle where the light would just skate across the surface and it reflects back down. It's almost as though the light is trapped inside. This is actually a pretty common effect, and it is exactly how fiber optics work. Okay, so we're going to develop some mathematics here. So first thing we need to do is define a brand new quantity, something called the index of refraction. It is a ratio of the speed of light in a vacuum to the speed of light in the new medium. Now, it's a number that's always greater than or approximately equal to 1, defined as 1 for a vacuum, and it has no units. There's a bunch of different examples. A vacuum is defined as 1 because that's 1. It's C over C, which is 1. Air is approximately 1, slightly greater than 1. It's like 1.0000 something. And of course, it would depend on, the density, temperature of the air. Water, regular water, tap water, has an index of refraction of about 1.33. Glass, about 1.5. Polycarbonate, which is the kind of plexiglass, kind of plastic that's used in eyeglasses, is about 1.67. If you have really bad eyes, they will often try and sell you something called high index lenses, which can be a little bit higher than that. A little more dense, which means that they don't have to be as thick. Diamond, significantly greater, and we'll talk more about why diamonds shimmer in a little bit. But diamond's index of refraction is about 2.4. Now, the mathematical relationship, I'm giving this to you without deriving. If you look a little bit later in the slides, you'll see that I have derived it. It's a bit of a complicated derivation. We'll talk about that later. But the thing down below, the primary equation for Snell's law says that n1 times the sine of theta 1 equals n2 times the sine of theta 2. Now, deconstructing that, theta 1 is the initial angle, theta 2 is the refracted angle. N1 is the index of refraction outside, N2 is the index of refraction inside the new medium. So what this actually says, this law of refraction, it states that during refraction, the product of the index of refraction and the sine of the angle remains constant. It's actually sort of a conservation of energy type idea. It's a little more sophisticated than that, but that's the gist of it. And there are some other really useful forms of this equation. Like, for example, you could just simply say that the ratio of the indices of refraction, n1 over n2, is inversely to the ratio of the sines of the angles. n1 over n2 equals sine of theta 2 over sine of theta 1. If you like, you could also say that's equal to v2 over v1, speed inside over speed outside. But everything there can be embodied in Snell's law right here. So just to do one little sample problem for you, and you have to have a calculator for this, obviously, and you have to be in degrees mode too. So when a beam of light enters water with an index of refraction of 1.33 from air, index of n equals 1, what's the angle of refraction? Well, if the initial angle is 40 degrees, then we can calculate the refracted angle pretty easily. We're going to use Snell's law. So how does that work? Well, n1 sine theta 1 equals n2 sine theta 2. n1 times the sine of 40 is going to be equal to n2 times sine of theta 2 unknown. Plugging some numbers in, 1 sine 40 equals 1.33 sine theta 2. Or sine theta 2 equals 0.48, and then on your calculator you want to do inverse sine of 0.48, and that will give you 28.8 degrees. And then finally, to get the speed of light inside the water, n equals c over v, we're solving for v, which is going to be 1.33 equals speed of light 3e8 divided by v. Do a little bit of math and you end up with 2.3 times 10 to the 8th meters per second. So even though the light goes from air into water, it is actually slowed down a good bit. 2.3 times 10 to the 8th is still fast, but that's actually just about a little bit more than 2/3 the speed of light in a vacuum. Okay, more to come.